Hello, my name is Dr. Malissa Lightfoot. I work for the Air Force Research Laboratory's Rocket Propulsion Division, and I'd like to talk to you today about combustion at near-critical thermodynamic conditions. I've chosen to focus on the near-critical regime because it's an area where crucial foundational understanding related to combustion remains unknown, and I think it offers an exciting scientific opportunity. Furthermore, the unique behavior that occurs in this near-critical region may enable exciting advancements in the design and operation of turbine, diesel, and rocket engines. Near the critical point, many properties important to combustion exhibit anomalies, including density, specific heat, and compressibility. The latter two of these properties exhibit singularities, becoming infinite exactly at the critical point. The extreme increase in compressibility leads to large sensitivities in density, so that small changes in pressure and temperature can have large impacts on the density. That means that the pressure head on even a small experimental cell may appreciably alter the density within that cell. That complicates terrestrial measurements, leaving large uncertainties in properties and thermodynamic conditions, as well as promoting convective stirring. Therefore, performing experiments in a microgravity environment is crucial to making progress in the near critical combustion regime. Performing experiments in this near critical region is important because we currently don't have adequate property models here. Even though current and future engines are likely to have localized areas within this regime, we're currently treating them in a very ad hoc manner. Now, this knowledge gap really prevents things like computational fluid dynamics from being good predictive tools, and it prevents us from performing optimizations. Furthermore, if we can understand and model the unique behaviors that occur near the critical point, then we can leverage them to improve the performance, emissions, lifetime, and other aspects of engine operation. For example, combustion instability is strongly controlled by the speed of sound and therefore the compressibility. If we could tune this compressibility, we could prevent these instabilities and the catastrophic engine damage that they create. You see two examples of that engine damage below. On the left is turbine engines, and on the right is a failed rocket engine. Combustion instability is the number one risk for rocket combustion chambers today. If we could tune for this, we could develop engines cheaper and we could make them more efficient because currently we have to trade off between lower performance and the needed stability margin. To explain why we do not have good models currently and what the open questions are, it's important to explain why fluids behave differently near the critical point than they do well away from it. These anomalous macroscopic behaviors that I discussed earlier are driven by changes at the molecular level. As the critical point is neared, the correlation between molecules increases, and the distance over which correlation occurs becomes infinite exactly at the critical point. In other words, very near the critical point, the position of a molecule on one side of the room is correlated to the location of a molecule way on the other side of the room. In contrast, away from the critical point, the scale of this correlation is on the order of nanometers, very much at the molecular scale. This increase in correlation leads to molecular structure. That's shown in the box on the right, while the box on the left offers the view of the molecular distribution well away from the critical point. These two boxes are snapshots of two-dimensional molecular dynamic results. This structure shown on the right prevents the simplifications that we typically use in our mean field thermodynamic models. Well away from the critical point, the small correlation length and the lack of structure, as shown on the left, mean that we can average the molecular scales and we don't need to treat them explicitly. Asymptotically close to the critical point, the correlation length is infinite, and we can use that scale invariance to reduce the dimensionality and create simpler models. However, in the near critical region between these two extremes, the correlations are too large to make averaging reasonable, but they're not sufficiently large that we can assume invariance and reduce the dimensionality. Therefore, a wide range of scales must be considered, and this complicates the development of models. The structure shown here is not static in time, and this brings additional complications. The previous figures were instantaneous snapshots. In practice, structure leads to temporally and spatially finite fluctuations in the number density and other properties. These fluctuations lead to the anomalies discussed at the beginning, and they also can be macroscopic in scale themselves, producing unsteadiness in measurements. Beyond just changes in property values, these fluctuations require changes to the hydrodynamic models, as initially shown by Landau and Lifshitz. That means that the Navier-Stokes equations require additional fluctuating terms. Now, those additional complications are not things that combustion researchers today typically consider, but they are important in this region. Additionally, these fluctuations require that longer times are needed to reach equilibrium, and larger volumes and longer time spans are required to produce statistically significant averages. Stated differently, the equilibrium assumption, which underpins the vast majority of the thermodynamic relation and property models which are used in combustion, may no longer be applicable. Defining a subdomain and quasi-equilibrium a la Onsager may also be very difficult or impossible due to these fluctuations. That is particularly true when there are two or more molecules present. Mixtures can exhibit a number of different complications because now there can be two types of structures. There's a larger structure, which I showed earlier and is reproduced here on the left, as well as the potential for a smaller structure, which is shown on the right. This is a notional close-up of a single cluster, and in this example, the light molecules want to preferentially group around the dark molecule, while other dark molecules want to be farther away from one another. These two scales of structures lead to fluctuations in concentration and density independent from one another and on different scales. This interplay between these two types of fluctuations are what make compressible mixtures unique. And this is an area that has received very little study. To date, most studies, including the earlier microgravity work, have examined only density fluctuations, which are present in pure substances, or concentration fluctuations alone, which is what happens when you have an incompressible mixture. However, in a combustion environment, you are going to see compressible mixtures, which means fluctuations in both concentration and density may be simultaneously present. These are going to evolve differently as the mixture moves through thermodynamic space, and their evolution will change as the composition of the mixture is varied. Now, currently, there is a lack of data relevant to combustion-related mixtures, and that makes creating and advancing models very difficult. The limited models which do exist for this crossover region, including equations of state, are developed from the standpoint of pure substances or simple ideal mixtures which do not represent the combustion environment, and it is unclear and unlikely that they can be used in the combustion situation. Overall, then, I see the area of near critical combustion as one with many interesting scientific questions, where the answers to these questions have the potential for impacting terrestrial and space applications. I'd like to leave you with a general summary of the needs I see in the area and a high-level view of those potential impacts. Many of the behaviors of compressible mixtures near the critical point are insufficiently known and understood. This includes items such as the range over which near criticality occurs, how mixture behaviors differ from those of pure substances or incompressible liquids, and how preferential association, as shown in the previous slide, impacts interfaces, diffusion, mixing, and other processes required to begin and sustain combustion. The applicability of equilibrium assumptions, which underpin traditional thermodynamic models, also remains an open question. And if equilibrium treatments are not justified, what type of non-equilibrium approaches are best suited to the combustion problem? I did not discuss the details here, but the molecular structure shown earlier could have an impact on reaction rates due to changing the collisional rates as well as the collisional energies. So, are pyrolysis, soot, and low temperature oxidative reactions affected in the near critical regime? Once the answers to these questions are known, they can be combined into better property models and affordable predictive tools. This is an important step to making impacts in both terrestrial and space engines because design tools need to be more predictive to reduce the cost of development and allow the optimization of devices. Furthermore, if we can learn how to leverage the unique behaviors that occur in the near critical regime, we have the opportunity to improve the performance, emission, lifetime, and other aspects of engine and combustion device operation.